as I mentioned, the mass moment of inertia is a property of its mass and its geometry. How far is the mass located away from its rotational axis? So I have this example here of just a blob, and if we take a look and we break this down into small components, so this is just a small differential element, and it has the mass dm, just a small bit of the mass. And then if we have the axis of rotation, which goes right down the center here, we know that the radius here is r. So if we want to find the mass moment of inertia of this entire object, what we need to do is sum this up over the entire mass, and it's r squared dm times dm. Okay, and that's the moment of inertia about this axis here. Okay, so with that being said, if this has a constant density, if every single particle is made of the same material and it has the same density, we can pull that out as well. So we have this is equal to the density times, and we integrate now over the volume, r squared dv. All right, because we know that the mass is equal to the density times the volume. So we've just pulled the density out, and now we're integrating over the volume. So those are the calculus-based forms of the mass moment of inertia. So, but in this class, we'll mostly be looking up values in a table. And I have included that table here. And let's take a look at that. So these are the moments, mass moments of inertia for different objects, right? On a sphere, no matter if you rotate about the x, y, or z axis, it is 1/5 or 2/5 mr squared here. All right, a cylinder, depending on how you're rotating it, if you're commonly rotating a cylinder about the z axis, and that is 1/2 mr squared. Okay, so that would be the mass moment of inertia rotating about the z-axis. It would be different for the x and y-axis. So with that, if we want to find the mass moment of inertia of an object rotating about, let's say, a cylinder rotated about, I don't know, some arbitrary axis over here, right? So some arbitrary axis system located a distance away. So we can use the parallel axis theorem again, and it has a slightly different form where I is equal to Ig plus m times d squared. Okay, where Ig is the mass moment of inertia about its center of gravity, or its centroid, right? We talked about the middle point. And then we add its mass, whatever mass this cylinder would be, times its perpendicular distance from that axis. So if we're talking about the y-axis, the perpendicular distance there would be this. This would be d, if we were rotating about the y-axis here. All right, so this is a way to use the parallel axis theorem in the mass moment of inertia. Okay, another term we use is the radius of gyration. Radius of gyration. Did I spell that right? Yeah, okay, and we use the value k, and it has a unit of length here. And k is nothing more than equal to the square root of the mass moment of inertia divided by its mass. Okay, so if we're given the radius of gyration, we can find the mass moment of inertia by mk squared. Okay, so when is the radius of gyration helpful? Let's say we want to solve the problem multiple times, and we have the same cylinder, all right, the same cylinder, but we have different materials each time we want to solve it. So it has a different mass, let's say. All right. The radius of gyration would be helpful because we could solve it, right, and just insert different masses for the same cylinder here.